We're excited to have you with us as we dive into our topic for today on how to operationalize a Gurobi price optimization notebook. I'm Renuka Goff on the product marketing team here at Nextmv, and I'll be your host for today. Our presenters for the session are Jerry Yurchison, Senior Data Science Strategist at Gurobi, and Ryan O'Neill, co-founder and CTO of Nextmv. To kick things off, we'll talk a bit about the intersections of data science, decision science, ML, and OR. Then we'll jump into a demo of the price optimization notebook, and that will include a scenario test and a workflow in Nextmv. We have a packed session today, so we'll do our best to save time for questions at the end. So please ask questions throughout the presentation, and we will make sure they get answered, whether that's live during the call or via email afterwards. You can use the chat or Zoom's Q&A feature. We will monitor both. Just make sure that you toggle between hosts and panelists and everyone, depending on who you want to see your question. All right, so let's jump right in. If this is your first time attending one of our talks, we're glad to have you. I'll give you a quick introduction to Nextmv. Nextmv is a decision science platform that acts as the hub for all of your optimization work. And the platform accelerates decision science and data science teams with decision ops tooling, which includes simple deployment, a testing framework, model management with a system of record, and more. We have optimization integrations with popular modeling tools and solvers. We will see that today with Gurobi. And we also have Decision App Quick Starts that, as the name implies, lets you get started quickly with pre-built models for common use cases like routing and scheduling. So now let's chat a little bit about ML and OR and the role that data scientists play in evolving the space. So Ryan, I will hand it over to you.
Thanks, Renu, and thank you, Jerry, for joining us today. It's really fun to put on this jointly with Gurobi and to chat about this exciting topic where we're sort of merging ML and OR. So to get the conversation going, let's talk about those two fields. So ML and OR are different traditions, though they do share some commonalities. Interestingly, often that's on the algorithmic or the mathematical side. What can you tell us about sort of the intersection of these two fields and their relationship to each other, and what makes this the right time for data scientists in particular to start picking up optimization and adding it to their toolkit?
Yeah, so it's a great first question, and I think probably what's on top of everyone's mind who's joining us today. So I would say that one of the more important intersections between anyone who is a data scientist or anyone who's an operations research analyst or anything in between or to the left on the whole analytic sort of spectrum is the intersection is problem solving. We're all trying to solve problems. But what sort of the traditional operations research and specifically mathematical optimization, the problems that they solve are just tend to be kind of different than the problems that machine learning and traditional data science and even more modern data science sort of techniques solve. A lot of the machine learning stuff lives in the predictive world, telling you what's next, what's going to happen, and what is my future going to look like. But operations research, and again, specifically mathematical optimization, is great for telling you what to do with that information. How do I build around this demand forecast that I have all of a sudden? And I think a couple reasons why it's really good to sort of dive into this now is two things. One is there are a ton of industries in which like mathematical optimization is already sort of widely adopted, and it's just the crossover between optimization and data science just hasn't quite happened yet. And so there's so if you're a data scientist and you want to do something new, then there's probably an opportunity for you to pick up optimization. And if you are an optimization expert and you want to do more stuff, there's probably an opportunity for you to do some machine learning or things like that to really sort of merge the two together into solving one problem. And I really think that, particularly for like the data scientist person, this like picking up optimization can be a real sort of career sort of differentiator for you. A lot of people are going to be doing the same stuff. Okay, I'm really great at tuning machine learning models. I'm great at LLM designing them, RAG and all that sort of stuff. And, I'm great at all that. And that's going to be sort of commonplace for a lot of, data scientists, AI engineers and stuff. Not a lot are going to be able to say that they know mathematical optimization and know how to use it. So I really think that now is a great time for that because the problems are all sort of merging together. The acceptance of sort of AI techniques for decision making is becoming more widespread, and people are believing this stuff a little bit better, more deeply. So it seems that now is the time to sort of be able to do all of the above. You want to do predictive analytics, you want to do prescriptive analytics. So yeah, now's the time.
Yeah, that makes sense. It's almost like a sort of like a full stack data science kind of role.
Yeah.
From the reverse direction, like when I was studying OR and I started working in it, one of the biggest things that I wish I had more training in was actually data science. So I can kind of
Hmm.
definitely see it going both ways.
Yeah.
Um, both of our, both Nextmv and Gurobi are seeing more and more data scientists start to do optimization.
Mhm.
Um, in from your perspective, what are the biggest challenges for data scientists that are trying to
Mhm.
pick it up as a field? And how can we in OR make this easier?
Sure. Yeah. I think the probably the number one thing, considering if you sort of think about the your typical data scientist is still nowadays still not someone uh, who has gone through a degree in data science. You're kind of coming from something that could be a math field or not. You could be coming from something that is completely different. You just really love data, and then you sort of work your way into it, and it's a skill that you sort of pick up along the way. So because of that, sort of if you say, I want to learn linear programming, or I want to learn mixed integer programming, or I want to learn something like that, you're going to get in the wilds of the internet, you're going to get hit with math right away and heavy math. And that can be either intimidating for some people, or even if you're like, okay, I can do this, it's still a big time sink. It still takes a long time to sort of deal with all of that. So I think that's sort of the biggest hurdle that I see. And from the OR community perspective is let's figure out ways that we can sort of reduce that, make things easier to just jump right in, and start optimizing right away so you can see the value of optimization, and really help people be able to communicate um, the value of optimization, how it fits into everything, the different types of problems that it solves, and sort of where its places within decision making, where it lies. And I think another reason that data scientists maybe haven't heard of optimization, or haven't picked it up is over the last 15 years, there's always been this new shiny analytics object. It could be classical machine, what we now can call classical machine learning. And then that sort of shifted into deep learning. Everyone needed to do that, and now everyone needs to be doing generative AI. There's always something that sort of sucked all the oxygen out of the analytics room, and never left much of a space for optimization. So that's another reason why I think why optimization maybe hasn't gotten the spotlight yet. But again, it does great things. It brings real true value to businesses and decision making. So there's definitely a room for it.
Yeah, anytime somebody asks me what I do, I always start with, well, back in the 1940s. And then the
That's the perfect
conversation
way
sort
to
of,
It's the perfect way to start it. Yeah, I love it.
right. Um, So I've done a few projects now with Gurobi Machine Learning, and I think there were the two most shocking things to me about it. One was just how easy it is to just take these like scikit-learn, PyTorch, other kinds of models and just like plug them into a MIP, and it really does feel magical. The other is that I had just never even, and this is just showing sort of my own lack
Mhm.
of foresight probably, but I just never even considered doing this before I learned about it.
Mhm.
And if you sort of step back, like there's no reason learning optimization that I couldn't have taken it just a regression or something like that and plugged it into an optimization model. You could do that with a nonlinear solver. And so it's sort of interesting to me that like, we pick up our Wayne Winston or our Hillier Lieberman books, and this isn't something that we're taught to do, or at least we traditionally
Mhm.
haven't been. So can you talk a little bit about why Gurobi is investing time in this now,
Mhm.
and what makes this the right time for these tools?
Yeah. So I think with a lot of sort of new things that come about, it sort of stems with work in academia, sort of people sort of, hey, this would be a cool thing to try and do. I wonder how it works and everything. And sort of that sort of started, probably like 5 or 6 years ago with a few published papers and that's sort of where people on the Gurobi side sort of started to get a little bit of interest in, hey, this would be something that would be pretty cool to do. But with that, there are a lot of, sort of all of those papers and those instances were very sort of, there'd be very specially built sort of like Python packages or very specially built sort of tools to solve that individual thing. There wasn't like this sort of broader framework to help sort of, okay, I want, I have scikit-learn sometimes here, I have XGBoost, I have this, to be able to sort of incorporate all of those things. That just, that wasn't what was out there. So that was part of our motivation, was to bring all of that sort of under one umbrella. But I also think that the technology and I mean technology in terms of the solvers that exist, particularly Gurobi, our solver, we feel great about it, obviously. But the technology there and also in hardware has improved to the point in which you can actually sort of, whenever you incorporate a trained machine learning model into a MIP or into an LP or something like that, it does drastically, or it can drastically increase the size of your problem, just how it works. But now the technology has gotten to a place where it's cool if that happens and it's not a big deal. It's not going to take your problem and make it, something that would run very quickly. And then now it just never converges and now you get no solution. Like that's probably not going to happen. So because of that, it just becomes more tractable. And that's sort of just the natural progression of how sort of operations research and sort of MIPS in particular, like the history of that is the theory was again in the 40s, 50s, and that's when that stuff started beginning to be developed from the theoretical side, but the applications of it really weren't until the 80s and the 90s because the technology finally caught up, and we're sort of at a similar sort of thing here where, all right, yeah, the technology is great, now we can actually do this.
Yeah, I mean, this just seems to be the trend is bigger models faster
Yep.
with more interesting stuff in them.
Hmm.
So I think that's probably enough of me like throwing questions at you. Let's now look at something real. So I'll go off video and hand the reins over to you, Jerry, to give us a better
Great.
introduction and show us some stuff in action.
Great. Cool. Thanks. Great conversation, great questions. I always love chatting about this kind of stuff. So what I'm going to do now is I'm going to take a little bit of time to give a little bit more of background of what Gurobi Machine Learning is and how it can work within price optimization. So Gurobi Machine Learning is an open source package that we have that anyone can sort of use in conjunction with any Gurobi Pi model that you have. And so it's really easy, lightweight thing to sort of just to add on to an existing model. But I'm going to sort of talk about why we want, where it sort of fits in, and where machine learning and optimization sort of fit together as a whole. So you sort of think of, I'm going to talk about three ways that machine learning and optimization sort of coexist and work together. Anyone who's actually trained a machine learning model, you have done optimization. Optimization is under the hood of everything when it comes to machine learning, because if you think about what you're really doing is you're minimizing some loss function, whether it be error or whatever it may be. You're minimizing some function. There you go. There's optimization. So the two are working hand in hand there. Sort of the most common way that we see machine learning and optimization work together is you take the output of a machine learning model, some sort of numerical prediction, some value, and you then take those values and then use those as parameter inputs, constant inputs, numbers within your optimization model. So you have a prediction of demand forecast for your product, and then that gets fed into an optimization model. So it's like a sequential thing, and that optimization model will then use that demand to build your sort of your optimal an optimal supply chain network to make sure you do things at minimal costs. What we're going to talk about today and sort of how this and how Gurobi machine learning works is we're talking about embedding, taking sort of option one and sort of flipping it around a little bit, embedding a machine learning model inside an optimization model. So talking about sales and demand. Well, if I increase or if I change my price, I'm going to change the amount that I can sell. So I have something where my decision variables can also be my decision variables and optimization model can also be a feature in a regression model. So that's sort of where the sweet spot that hits here. So I'm going to talk about this specifically within the context of price optimization. So what is the optimal price that maximizes our total revenue for a particular problem? So let's say P is the price that we set and D be the resulting demand. Well, we want to talk about revenue. So revenue, you can think about revenue as, well, the price that you charge times the demand that you'd have, and that would help you understand what your revenue is. But if you think about how you can change your prices and how that will affect demand and affect revenue, if you keep pushing your prices up, 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 then your demand's going to go down, 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 and likely your revenue is going to go down, down, down to zero if your price is too high. Think about the other way. You put your price too low, your demand is going to go up. Yes, that's great, but again, your revenue is still going to go down closer to zero. May not be actually zero, but it's still not going to be great. So if you sort of think about this in the sort of the structure of a mathematical optimization problem, we want to maximize our revenue subject to some function that relates price and maybe other factors to demand. And then, so that's the first equation that we have for our in our constraints. And then we also have a bunch of other business rules that I'm sort of representing by a general function h. So that could be all the other things that we need to take care of in our supply chain or whatever problem you're trying to solve. But we have this relationship between price and demand that we want to actually be part of the optimization model. And let's say that your data look like this for your single product or something like that, and this is what your price and demand data would look like. You'd probably look at this and be like, this is simple. I got it. What I'm going to do is I'm going to fit a linear regression model, make that the constraint, and there you go. And not only is this easy to do, it works and keeps everything linear, which is a nice thing for mixed integer programming. Doesn't need to be linear, but it could be helpful if that's the way that it works. So great. If your data looks like this, then okay, you can look at this and say, I still got this. Okay, now I could fit a curve here, and now I have now I can represent this function as the equality constraint, and there you go. Now I have my complete price demand relationship sort of taken care of. And by the way, these types of functions, nonlinear things, which are a little bit more complicated, sometimes this is sort of could be easily modeled within Gurobi 12, either with the general constraints that will talk about sort of logistic functions like this, very sort of very easy to deal with, but then also composing these types of functions is also much, 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 much easier, and a great way to add this sort of complexity to any model. But anyways, so if this is the case that you're in, you have a nice, you understand what the sort of the general sort of framework of the relationship between price and demand is. Great, you can have sort of some function that represents that, and then you're putting more information into the optimization model so it can make more informed decisions. Well, what if you don't know this? And you're sort of thinking, okay, well, I have a highly complex relationship between price, demand, and all these other factors I need to consider. This is where Gurobi Machine Learning really helps. So you can take that sort of this unknown sort of structure of the data and how price and demand and all this sort of stuff fits together, and you can think of it as a black box. And a great way to sort of represent a black box in a sense is through a trained machine learning model, trained regressor. So this is particularly what Gurobi Machine Learning does. Is it handles the relationship between the decision variables and regression features in just a few lines of code. And I'll sort of talk about what this is in a second, but I really want to clarify how this is different from sort of option 2 that I talked about earlier on just a couple slides ago. Typically what you would do here is you would iterate through a bunch of price demand sort of pairs. You say, okay, if this is my price, this is my demand. And then use that as parameters for an optimization model to make sure that you maximize revenue subject to all your other constraints, and you would iterate through that a bunch of times possibly. So essentially, all the information that you're giving it is a few or maybe a bunch of, but still not all of the price demand pairs, all of the price demand information that you have through the machine learning model. But what you can now do with this package is you can give all of the information at once to let your optimization model really make a truly optimal decision based off of the entire relationship and not just bits and pieces that you'll feed it. So this is what I think is really cool. And if you look at sort of the bottom of here, we have the one line of code that I'm sort of highlighting at this point. To really do this, there's a couple other things you need to do before, and we'll look at this in the notebook. But the main sort of function that you need to use for this is just this one function called add predictor constraint. The letter M represents some optimization model that you've already defined. Reg is some trained regression model that you have. Feats is just your features of your regression model, in which these will also contain Gurobi decision variables, and then D is the output decision variable, sort of the output of your machine learning model. So you might be thinking, all right, this sounds pretty cool, but how can I use this? What sort of machine learning frameworks are available to me? Well, a lot of them. And this is sort of what we think is what's really cool about this effort is, again, I mentioned that you could find some of these, you can find out there like something that does this for a few scikit-learn things, and then maybe some other scikit-learn things. And then, you sort of find all these disparate, but now we sort of brought all this under one umbrella for Gurobi Machine Learning. And so anything you see up here is what you can use as a regression model for your problem. So this is what I think is quite cool at this point.
If I could just add one thing to that,
Yeah.
that previous slide that I just I was thinking about while you're saying this. I've been in places where we did forecasting for like thousands of different regions, and we would use different technologies on here for different cohorts of regions because they would get us better accuracy.
Exactly.
And then we had to do like a predict then optimize kind of thing where we would predict out a demand point and then optimize. But if we had access to something at the time like Gurobi Machine Learning, we could have actually just ingested different kinds of models, and that would have been really cool.
Yeah, and it makes it exceptionally easy because going back to this one line of code, all you really do is just replace the second argument with whatever machine learning model you've already trained, and it makes it sort of so easy to plug and play. So I'm going to give a little bit before we dive into a notebook about this. I'm going to give a little bit of a background so I don't have to sort of churn through all the text of the notebook, and we can sort of dive right into the code right away. So we're going to talk about a price optimization example. We're talking about competing products with a fixed total capacity. So what I mean by that is you have a set of categorized products. Each product sort of takes up the same amount of quote unquote space, and total space is limited. So what I mean by that is a couple examples would be actual physical sort of shelving. I have products that I want to put up on my shelf. So I want to find out what's the right balance of sort of the more expensive things or the top products versus the not so great ones that people still like to buy, so on and so forth. And then also you can also think about pricing airline tickets. You have, if you're trying to book a flight, different seats cost different amounts of money, and what's the right pricing that I should set for different sets of seats in order to sort of maximize my revenue. So you can sort of see how each of these sort of fits those three descriptors that I sort of just plopped up there. So we decide the prices for each product, and then these decisions, along with other factors, obviously, will set the demand. So going back to what I was just talking about, we can then relate the price and these other factors to demand with some function and estimate that function, be it with the machine learning model. We must adhere to other business rules. We want to make sure that our first class airline tickets are not less expensive than anything else. They need to be the most expensive, and they might need to be the most expensive by a certain amount. But again, the goal is to maximize the potential revenue. And sort of for the notebook that I'm going to dive into in a second, we're going to have just two products. The total space, again, that we have is going to be 200 units. It could be 200 seats. It could be 200, whatever it may be. And P sub C is going to represent the price. And then N is going to represent the number that we decide to assign to a certain category. So let's reconnect, and I'm going to run all of this and run it anyways. Okay. If you go to, we have a link that we're going to share for this notebook. And if you go to that link, you'll click one click away and you'll come up with this. And what I'm going to just dive right into is, let's look at the data that we have for this. I've already outlined the problem. So the data that we have is sort of fictitious data that we came up with that relates and we have two products. It relates the price of product one, the price of product two, and the number of product one that we sell. And we're gonna, again, since we have this sort of fixed capacity of 200 units, whatever we don't assign to unit or category one, we're going to assign to category two. So we're going to use all the space that we can. So that's why we don't really need to have an N2 in here. So let's look at what the data sort of looks like from a correlation perspective. If you look at the bottom left or top right, you see that the price of category one and the number that we assign to that is highly negatively correlated. Obviously, that makes sense. If the higher we set the price, the less we're going to sell there. If you look at price of category two, that's going to have a slightly positive correlation. Makes sense. If I increase the price of product two, people might lean towards the more might lean towards the other product, and particularly if product one is the one that we want to make more expensive, it's our high product, is our first class or whatever it is, it'd be like, okay, well, if the price is closer, then then it's worth it for me to maybe spend a little bit more. And then the prices themselves we're sort of having as uncorrelated. So if you're a data scientist, all of this is going to look, or even if not, anyone who's done any machine learning, this is all your typical import your sklearn stuff, split your training and testing data and fit and do and cross-validate and all that sort of stuff. So I'm not going to spend too much time here, but we fit a linear regression model, and we also fit a gradient boosting model. And here are sort of the scores for each of those. Look at. So I'm going to sort of start focusing on the optimization part of it. So I've talked about the background again a little bit more. So let's look at some of the parameters here. Again, C is going to represent the number of categories we have, which is 2. N is the space available, which we're setting to 200. And then now we have this thing called a price control parameter, and that's going to be lambda. It's fairly common to sort of have something like this as part of your problem. You could sort of think of this penalty term as something that's akin to things in like lasso regression or ridge regression, where you have a penalty term to make sure that you don't overfit. You can sort of think of this as the same thing. Our decision variables are P and N. As I mentioned before, P is going to be the price for our two categories, and is the number that we assign to each, the amount of space that we assign to each category. And we're going to have some basic constraints here. We're going to have a minimum value, a minimum number for each category. So in this problem, we're going to make sure that we have at least 50 sort of tickets or 50 units assigned to each category, and each is going to have an upper and lower bound for their prices. Specifically, product one is going to be between $300 and $400, and product two is going to be between $100 and $300. And then we're also going to, so that's essentially what this chunk of code takes care of. I also commented out here a slightly more concise way of writing that, where you're defining those bounds for the prices and number for each category, defining that explicitly within the variable definition. You can do it that way as well. But in general, we're going to have a constraint for our total space allotment. So we have 200 sort of units of space. So that means the sum of all of the quantities that we assign must be equal to 200. And we're also going to have an ordering for price constraint. We want to make sure that the price between category 1 and category 2 is between $50 and $100. So we're going to make sure that we have at least a $50 gap, but no more than $100 for our two categories. And then the objective contains two terms. One is the revenue term that you can sort of see right here, price times quantity, sum that up over the categories. And then we're also going to we're going to add this penalty term. So we're going to subtract off some lambda value between 0 and 1 times the sum of the prices squared as a penalty term. And we put a source that you can check out there to see sort of the motivation behind that. So we have our sort of what would be here typically, this is purely the optimization part of the model, the MO part. Now we're going to integrate the machine learning model. So all you need to do to do that, again, is install Gurobi Machine Learning package and import the predictor constraint. So again, I want to sort of focus on the fact that this package is really useful, or the use of it is when you have decision variables that are also features. So they have to have that intersection. So we create a pandas data frame that, if you remember from just a few lines above, we defined P as our decision variable. So we're actually putting in decision variables into our pandas data frame. And we're also giving the name, the column name for each of those to be the same name as what we used in the regression. We want to make sure that that matches up. So we're creating a data frame that contains our decision variables. And all we do, this should look pretty familiar from what we saw on the slide. We're adding a predictor constraint to our model M. This is the regression model that we want to use. This is the feature data frame that we just created, and this is the output decision variable that we want for our machine learning model. And what we want to print some stats there because we always want to see how this is going to influence our optimization. So this adds 90 decision variables and 30 linear constraints and 246 general constraints. If you noticed when I sort of did the gradient boosting model at the beginning, let's sort of scroll up to that real fast. The number of estimators is quite low. That's because we're trying to run this on sort of our pip install license that has a variable size, a variable and constraint limitation of 2,000 variables, 2,000 constraints. And if you're doing nonlinear optimization, it even limits it a little bit more. So I needed to sort of live within this world. So that's why, and you sort of see we add a decent amount of variables and constraints to a problem when doing this. So let's actually solve this because that's all we need. We're done. Now it's time to solve. If you used Gurobi before for nonlinear problems like quadratic and non-convex things, you may have noticed that you would have to set a non-convex parameter to 2 to do stuff like this. That's not necessary with Gurobi 12 and onwards. I left it in there because it still is something you can set and it still may help. But check the documentation if you want to know what you want to do there. But so we optimize, it does some work, typical Gurobi stuff, and there you go. We print out the optimal price. So for category 1, we're going to set the price at almost 265. We're going to set the price for category 2 at 300. We're going to use 91 units of space for category 1, 109 for the second, and we get our total revenue. So we've successfully incorporated a machine learning model into a broader optimization model. That's great for us. It's awesome. You may be thinking, well, you just used like sort of 1 point. What about uncertainty? There's always uncertainty in demand forecasts, and it's something we always need to consider. And that's 100% true. I do not disagree with that in any way, shape, or form. But there are other ways to build. There are ways to build that into the optimization model, running multiple scenarios. And as we see, running scenarios on the Nextmv platform is also easy to do. So there's a bunch of ways to sort of to deal with that. And you can also build more complex optimization models that are stochastic programming or robust optimization, whatever it may be. There are ways to do it. We're keeping things a little bit simple here. So keep that in mind as you sort of think about this example. So that is the notebook. What I want to talk about now is how can we next movify this? How can we actually put this, operationalize this, and how much sort of lift is that going to take? And the answer to that is not a lot. using notebooks is a great way to sort of sort of build proof of concepts, and it's just sort of a standard way of doing modeling nowadays. And Nextmv realizes, and we at Gurobi also realize why we have all these notebooks, that's a great way to work. So to sort of get this going in Nextmv, all you really need to do first is connect to your account with an API key. So you just sort of put the little secret in here and then hide that away. And I'm not going to talk in a lot of detail about what's going on line by line of the Nextmv code. They have tutorials on that and have walked through that. So to dive into that in more detail, I'll allow them to talk about that with their own resources. But for me, it was easy to pick up. And I just want to highlight sort of where this happens, where the changes occur. So you do have to install a couple different sort of Nextmv packages, one specifically for Gurobi Pi, same thing for scikit-learn. And all of this good stuff happens. All of these are successes. Yay, we did it. Cool. And now this looks very much like the typical notebook that we had, and most of it is. All of this is exactly the same. The data stuff, the what's in there, the correlation plot does change a little bit because Plotly works very nicely in the Nextmv platform, which we'll see in a little bit. So in order to sort of bring that over, change this to a Plotly plot, and again, it looks nice. All of this exactly the same. Building the predictor, all of this sort of stuff to see, to fit, to test, to train, to all of it. All this is great there, and exactly the same. So now let's next movify the machine learning model, and here's where you sort of see a little bit of the new code. We do need to import some of the modules from the Nextmv sklearn sort of package, but then essentially what we're doing here is we need to define inputs and define options, what we want to sort of mess around with for the machine learning model, and then what do we really care about for output. So this here is defining a function to help with the inputs and starting defining options. So that's about it there. That's all we really need to do. This part is exactly the same, and here is where we actually start doing a little bit a little bit more. There's a little bit different code here, but by and large, it's exactly the same kind of stuff that you would do in training and operationalizing a machine learning model. We do have a few things that we want to make sure we keep track of, for cross-validation scores and what the outputs are that we really want to keep track of over time. And then this is the same thing that was for the linear regression model. Everything's the same for the XGBoost. Here we have a little bit of code to put the Plotly plot up in the dashboard as well, since we're interested in that for the correlation matrix. And that's really it for most of operationalizing it. Now we can run the model locally to make sure that everything's working the way that we'd like. So we set some of the options. This is essentially setting the mode of the regression model that we want to be either linear or XGBoost. So we're setting it to be linear for now, and writing the output. So let me scroll up to the top of the output. There you go. A lot of the stuff with the coefficients and everything. This is what you would expect in typical machine learning output there. So let's scroll down there. Now the next thing to do is actually let's push this to our cloud account. And to do that, again, it's these two blocks of code to push the machine learning model. So very easy and lightweight to do, doesn't take a lot of extra work, and it all just lives within the same notebook very natively. So again, I'm not going to talk about all this bit by bit, but essentially we're just defining a few things, defining our requirements, and then pushing that to our platform. So you get all these cool emojis of success, which is a great thing to see. And then you can also then run this remotely from the notebook on the Nextmv platform and see that, make sure everything is working the same way as it did before. And we scroll to the top of the output there. Again, everything looks exactly the same. So congratulations, we just operationalized our machine learning model. And then as you can think with the optimization part, it's all pretty much the same. same text, same code to sort of understand and write the model. All this is the same. Let's keep scrolling down to actually now, how do we operationalize this optimization part? Here we finally get a little bit of different code where we have to we're sort of here we're defining our sort of static inputs, and again the same type of code where we're defining what options we want to have for this model. And here's one that we're setting for, I'm highlighting here towards the middle of the screen, is this the lowercase l. We're using that for the lambda value, so you can define that as one of the options that you can sort of tinker with down the road. So Ryan, I have a question for you now. Sort of how easy is it to add a bunch more of these, or maybe you're interested in other options, maybe sort of Gurobi specific things or model specific things? Can you sort of just like chat about how that would work and what that would look like and what options people have?
Yeah. So typically when we're looking at the platform, we're looking at individual runs, and when you execute a run, you can set you have an input, and you can set configuration parameters. For Gurobi specifically and scikit-learn, we provide wrappers that allow you to take all the massive number of options and parameters that you can set in Gurobi and scikit-learn and things like that, and sort of map those to environment variables or command line flags that the cloud platform uses. So we sort of handle some of
Okay.
that orchestration for you. And then when it comes to sort of testing these things against each other and trying to figure out what the right configuration or how it performs on different inputs, when you run things like scenario tests where you have multiple runs, you can do things like vary those options. So like 1 through 5 or 0.1 through
Gotcha.
1.0. And you can do the cross product of all those different combinations. You can also change inputs and run input sets as opposed to single inputs, and you can do the combination of both of those things and get aggregate data out of all that. So it's fairly simple
Okay.
to sort of do whatever you need to do in those circumstances.
Cool. Awesome.
Good question.
So then, thanks for the clarification. And the last bit of Nextmovifying here is making sure that you're noting important things about your optimization model that you're interested in, particularly maybe the number of variables and constraints. Obviously, the solution is important, and then return that. And then the same stuff as before. You can run the optimization model locally. The Nextmovified version, run it locally, and then also use the similar types of the same stuff to push it to your cloud. And lastly, then running it remotely. So that brings us to the end of sort of the Nextmovified version of the notebook. As you can see, there really wasn't a lot of change there. It was all pretty much the same. So what I'm going to then sort of talk about is, okay, we push this to our cloud dashboard and everything like that. Like, what does that look like there, and what can we do there? So I'm going to hop into a couple things very quickly. I know I yammered on a little bit longer than I had hoped, but this is good stuff. So after you sort of push these models, this is what you would find on your Nextmove dashboard. So I'm going to hop into the ML regressor. You can again see a lot of the key statistics, history of runs and everything. I'm going to dive into one of these. And this is where you can sort of see what everything that happened within your run. What's the input? What are the results? And then again, if you have particular visualizations that you're interested in looking at, particularly maybe this correlation plot, you could then see this here for each run individually, which is really, really cool. So let's go back to the optimizer part of it. And here's where you can look into specific runs, see details on it. You can see the results. So what are the all the key stuff that you're interested in, any analysis and logs and stuff you can find here. And then you can also, so let me go back here. You can also look at some experiments. So maybe one thing that we didn't look at in depth is how that penalty term may change things. So you can sort of see how this penalty term impacts the objective, and you can dive into the individual runs, and you can obviously export all this data and then put it together, sort of look at things. But then you can see, okay, let's look at this run individually. What are the results? How did this decision what are the differences between these decision variables here and here? So this is a different different run. We end up with different prices and different space allocations. So you can sort of see how all this works together and see, okay, what's the right sort of lambda value for this, or what's the right other parameter value that we have. So and then lastly, we can sort of see how all this encompasses a workflow. We have an optimization part, we have a machine learning part. So you can also put this into a nice workflow and look at one of the runs there and actually come up with a nice visualization of how everything comes together. So you have the regression part, how that feeds into a translation layer, and how that feeds into an optimization part. And that's, again, so you can see how everything, how the machine learning part and how the optimization part all works together and lives under one happy workflow. So we're already sort of really high on time, so I'm going to stop here. I hope that was a nice quick rundown of the platform and how to Nextmovify things and all of it. So I hope that was really interesting. And I think we can maybe do a little bit of Q&A if we still have time.
Yeah, perfect. Thank you so much, both of you, for the great conversation and for the wonderful demo as well, Jerry. Really cool to see how these two technologies work together to kind of accelerate that development workflow. Okay, I'll just do a very quick recap here. So what did we just see? We saw Jerry walk through the Gurobi notebook. He deployed the ML and OR model to Nextmv. We saw those models in the UI. We looked quickly at a scenario test, which kind of shows us how we can configure different options and look at model performance with those different options. And we also saw a workflow, so connecting those two models that Jerry deployed into one orchestrated workflow from ML through OR. And I've got one more slide here on kind of what happens next. I won't walk through each of these pieces, but these are some considerations for what you might do once you have deployed your notebook to Nextmv. You can run some more experiments, consider using Python scripts, Git and CI/CD, and of course, sharing these results with stakeholders. So that's one really nice thing. Everything that Jerry shared there is something that you can grab the links for and share those with your teammates as well. And then, of course, promoting that new model to production and managing it with Nextmv. Okay, I know we are over time, but I'd love to squeeze in one quick question. This question came in during your slides, Jerry. I don't think there's necessarily one specific answer to it, but I think Jerry or Ryan, if you want to share your experience here, I think that'll be helpful. The question is, how do you get the demand price curve? The model could be easy to fit, but getting the data can be challenging in reality. Do either of you have experiences that you'd like to share there?
So getting the underlying data, getting the data that even starting to even to the left of where we started today. Yeah, that's yeah, that's always the problem. And there's a reason why there's a reason why for this notebook we made up our own data. It's because it's so hard to find out there in the world and in the wild. So yeah, that's the one of the first hurdles for any analytics project is getting the data, getting it in a form that's usable. And so when we create notebooks, we like to try and use real world data or something that is as close as possible because we want to make it as close to real as possible. Yeah, we couldn't find anything, so we needed to make our own. So I think that kind of sort of sums up the difficulty there. Yeah, I'll leave it at that for now.
Yeah, what I've seen in other environments, what we've sometimes done is if we have some data and we're expanding into, say, a new place where we don't have data, we would try to sort of estimate what it would be based on similar data that we have. So like if we're opening a new region, oh, this kind of looks like this other area, and so we might start with something like that. But some of it does come down to like, are you a frequentist or a Bayesian, and can you learn? Can you make an assumption and have a prior, and then sort of learn very quickly about the new about new probability distributions?
Wonderful. Well, thank you both. I know there are still a couple of questions unanswered. We will make sure to answer those via email, so not to worry there. And we will share all of the links to the resources that Jerry mentioned, as well as the notebook that he was working out of. We will email that to everybody along with the recording. So thanks for sticking around with us a little after. We really appreciate the conversation today, the questions, and the demo. So thank you again to both Jerry and Ryan. And we hope to see you all next time.
Thanks, Jerry.
Awesome.
Thanks, Renu.
Thanks for having me. I really appreciate it.